Hey guys, what's up? So I'm going to do a video lecture to kind of supplement for today. Like I said, I definitely do apologize for that, but I believe this video lecture should be enough to keep us caught up, and I'll spend the first kind of like 5 or 10 minutes of lecture on Friday to kind of take any questions on the rest of Chapter 8 and Chapter 9.1. So I'm going to do the first section of Chapter 9, so then we should be starting on Chapter 9, Section 2 on Friday. I will have your tests graded, and I'll have those back to you. I'm kind of in the process of grading those right now, so they will be graded, and I'll show up to class 10 minutes early on Friday. That way I have some time to kind of give those out and take any questions before we start the lecture for Friday. Okay, so on Monday, where we left off was talking about dilutions and the C1V1 equals C2V2 equation. And so the C1V1 equals C2V2, it's a very, very straightforward equation. Basically, it's just whatever the concentration multiplied by the first volume, and it's going to equal the second concentration multiplied by the second volume. So really the guidelines for that, plug and chug. Just kind of find what that first concentration is, what the second one is, and just find the variable that you're solving for, and then solve for that. Really just an important note about this is to be sure that whatever the concentration is in C1 will be the concentration that you'll get for C2. And so therefore, if you say you're solving for C1, but your V1 is given in, let's say, liters, and your V2 is given in cubic centimeters or some other form of volume, make sure that those two are the same unit, and then you can go through and plug and chug. And that's really the same for any equation. And if the equation includes a constant, then making sure that you include all of the units or use all the units that constant has, so everything cancels out appropriately. And so for this practice problem, I did this kind of like very quickly at the end of class on Monday, but I did it again right here. I will upload this document as soon as I finish up with this recording, and I'll upload it at the same time that I record this, that I add this recording to Canvas. And so for this one, we're looking for where's our concentration one? Well, our stock solution is always going to be our first concentration because we're diluting from there. So our first concentration is 2 moles, which is 2 moles per liter. So that's big M is molarity. And then what we're looking for is how many mils of this 2 moles per liter solution would we need to create 50 mils of a 1 mole per liter solution. So if you look at the right side of the screen, right over here, you can kind of see I've already worked this out. And so really your C1 is 2 moles, V1 is X, that's what you're solving for, C2 is 1, and V2 is 50. So another important note for the C1V1 equation, I think I mentioned it briefly on Monday, was that this V2 is your final volume. And so that final volume includes whatever you're going to be adding of each, either the original stock solution plus whatever your solvent is that you're adding that you're going to be diluting it with. And so in this situation, it says we need 25 mils. And so that doesn't mean that we need 25 mils and plus 50 mils. What it means is that we'll have 25 mils and we'll bring the total volume up to 50. So we would add 25 mils of the stock solution and 25 mils of whatever the thing that we're diluting it with. Okay? And so I'll push forward now to kind of these next few slides. And so these next few slides we're talking about oral medications and IV solutions, which includes flow rate. And so for oral medications, I'll kind of read through this. Basically, the dose calculations are performed using the concentrations of the medication and the amount needed. So really all this is it's stating that there's some amount of mass and some amount of volume. And so we've got mass per volume. And so we can use this as almost like a concentration. So this is a concentration. We have mass over volume. So then we can see, okay, what volume do we need? And really this is just basic dimensional analysis like we've used for the class so far. And so over here on the right side of the screen, I'll work this question out. So right here it says slide 37. We would need, kind of just like summarizing right here in these 3 bullet points, we need 500 milligrams for every 6 hours. And so the suspension concentration is given at 200 milligrams for every 5 mils. And so what we need to find is what volume will we be given to the patient every 6 hours. Well, we know that we need 500 milligrams for every 6 hours. We know that this concentration of the suspension is given for 200 milligrams for every 5 mils. So we can kind of set up this equality right here where we say, okay, we know that there are 200 milligrams in 5 mils. So if we have 500 milligrams, how many mils do we have? And so I kind of rearrange this to say, okay, 200 divided by 5 equals 40. So 40 equals 500 divided by x. So like I've said before, we can rearrange this where we take this x and flip it. So we'll take this x right here and flip it with this 40 right here. So now we have x equals 500 over 40. And so therefore our x is 12.5 mils, and that's needed to provide the patient with 500 milligrams. Since it says, that 6 hours, really that 6 hours isn't going to be used in the calculation, so that's kind of like a little bit of a distractor. But really what we're looking for is how many mils do we need in order to have 500 milligrams. So it turns out that we need 12.5 mils to provide that patient with 500 milligrams. And so in IV solutions, and in this flow rate, we're actually taking into consideration time. So in this one, we looked at, 6 hours, but for this IV solution in flow rate, we are actually taking into consideration time because we need to know, if we're giving this patient a specific amount of medication, over what amount of time would we need to give that, since an IV is kind of flowing at a specific rate. And so flow rate is really the volume over time. And so that's flow rate, that's the same for really everything, but specifically for IV solutions, that is the case. And that's really what we'll use in this class. And so dose calculations need to consider not only the concentration of the stock medication, but also the flow rate of the IV. So if we know we need to give a patient a specific amount of medication, and we know that we need to give it over a specific amount of time, then what do we need to set that flow rate to make sure that we're giving them that amount of medication over the correct amount of time. And so the rate really depends on the rate that the medication is prescribed by the physician. And so a lot of times what you'll get is an order that's given by the physician that says, we need to give this patient this much medication over this much time, and the concentration of the IV bag is this concentration. So then you have to determine, if I know that this patient needs this much over this amount of time, then you determine, what should I set the flow rate at to be sure that if I come back in, say, 6 hours, this patient has received exactly that mass of medication, And so units are usually given in milligrams per minute, micrograms per minute, or grams per hour. And what you'll see with this next example is that sometimes they're just given in units. So in this example, this IU, or international units, it simply just means units. And we treat it just as any other unit that we would use, And so even though it says units, kind of like, don't let that trip you out, really it's just, you can think of it as some amount, right? So in this last slide right here, we're looking at solution volume over time, and then the rate is prescribed in mass over time. And so if we're looking at this slide where we have units, then we're looking at some amount per volume, right? So some amount of mass per volume. So an order is given, and I've kind of worked this out right here over on the right side of the screen. So an order is given to infuse 50 units per hour of heparin, which is an anticoagulant. So what that does is it is a very, very common blood thinner. So it's used a lot, given to patients that need to have their blood thinned. A lot of times it's given for patients that have had a stroke or something to that effect. So that way we can make sure that the blood is not going to coagulate, which really just means kind of stick together. So it's thin enough to get through, all of the vessels and veins in the body. And so this IV bag that we have is supplied with a concentration of 250 units per 1 milliliter. So at what flow rate in milliliters per hour, right? So flow rate, we know it has to be volume per hour. Should the IV solution be infused into the patient? So like I said, proteins are sometimes reported as international units. So this heparin, it is actually a protein. And so we're going to treat this just as any other unit. And so over here on the right of the screen, you can kind of see how I've worked this out. I've summarized right here, as I did in the last one. We need to infuse 50 units per hour. The concentration of this to infuse is 250 units per mil. And the flow rate is what we're trying to find in milliliters per hour. And how much should that be infused into the patient? And so if we look at, we know that there are 250 units in 1 mil, right? And so that is given to us as the stock concentration. And we know that we need to give this patient 50 units per hour, okay? So then how many milliliters per hour do we need? Well, the first thing to really do is to say, if we know that there are 250 units in 1 mil, then just like the last problem, if we need 50 units, how many mils would that be, right? And so we can do the exact same thing. So we can say 250 divided by 1 is 250. So this would be 250 equals 50 over x. And so I did kind of skip that step right there since I did include it in the last one. And so then we can rearrange it to whereas, we can take this 250 right here and switch it with the x. And so therefore we have x equals 50 over 250. So therefore 0.2 milliliters contains 50 units. So therefore we need to infuse 0.2 milliliters into the patient every hour. And so that would be our flow rate. It would be 0.2 mils per hour. And so if we're looking at this problem, really this is like a very straightforward, simple problem. It's basically just saying, we've got this stock solution. How many mils would 50 units contain? And we know that we need to give it to them per hour. So you can imagine a step that this could actually go one step further and say we need to infuse, say, 400 units per 4 hours. So what would the flow rate be in units per 1 hour, right? So we can figure out exactly how many units, how many mils contain that number of units that we have. So say, for example, we're using 300 units, needs to be infused every 6 hours. Then we can find out how many units we need, how many mils we need to have that 300 units. And then we can divide to break it down to say, okay, if we need 500 units or, say 5 mils over 6 hours, well then how many mils do we need per 1 hour, right? So it'd just be like one step forward. So you can imagine this practice problem over here on slide 37. It's given 500 milligrams of amoxicillin every 6 hours. So what volume should be administered to the patient every 6 hours? Well, if we're looking for flow rate is going to be per time, and a lot of times it will be per 1 hour. It will give that to you in the question. And so it's asking, like in this question, the flow rate in milliliters per 1 hour, right? So per hour. So we would just take one more step further in this question right here, and we would go from, okay, if we need to give them 0.2 mils in 6 hours, well, then how many do we need to give them in 1 hour? And really it's just 0.2 divided by 6, right? And so that's really the extent of what we'll be talking about with IV solutions, flow rate, medicine, the rate at which the medicine is prescribed. And I'll upload a few practice problems and also upload problems in the back of the book. That way you can work through a few of these. And you can definitely ask me questions if you have any, okay? And so the next part 8.4, which is kind of like the last part of chapter 8, we're talking about osmosis and dialysis. And so osmosis is a little bit different than dialysis, but there are a few similarities. And so over on the right of the screen, you can kind of see I've defined osmosis. And so it's the movement of water from an area of lower solute concentration to an area of higher solute concentration. Okay, and so when we're talking about osmosis, we're really talking about water. And so I know it says, over here with the osmosis refers to the flow of solvent through a membrane to equalize concentrations. Osmosis in this class specifically, we're really going to be talking about it as the movement of water. And so osmosis and dialysis are a little bit different from each other in that dialysis is the movement of the solute and osmosis is the movement of the solvent, okay? And so what is this thing moving through? So we can talk about selective permeable membranes to discuss, okay, some membranes will allow water to get through, but not solute, and other membranes could allow solute to get through, but not water, right? And so dialysis, the movement of solute, we would have a selective permeable membrane that would only allow the solute to get through and would not allow the water to get through. And so selective permeable, it's just really exactly what it says. So it means really what it says. It's selectively permeable to only specific things. And so those things would be given to you in the question. So it only allows certain substances to pass. Now, this is a great example of a cell membrane. And so a cell membrane is very selective in what it allows to come in and what it allows to leave. And it needs to be like that, right? Because we can only allow certain things to leave, and if things diffused out down their concentration gradient all the time, then we would never be able to hold the nutrients in that we need. We'd never really be able to excrete the waste that we need to get out in order for the cell to work efficiently. So we will talk later in the class about cell membranes specifically, about their composition, the biochemistry behind it, which is the really cool stuff. But for right now, it's important to understand how a selective permeable membrane works, right? And in dialysis, I mean, I'm sure everybody's heard of dialysis before, right? If you have kidney failure, you need to remove some of the waste products that your kidneys normally remove, and you need to remove that efficiently. But if your kidneys can't do it, then we have machines that can filter that out. And so the most important factors in determining whether a solute can go through a cell membrane are size and polarity, okay? And so cell membranes specifically, just very like macroscopic right here, talking about not really the biochemistry, but just kind of point blank things to memorize. Small non-polar molecules are allowed to get through. We know O2 is nonpolar, we know CO2 is nonpolar, and we know N2 is nonpolar. The reason for that is because of the electronegativity. There is no difference in electronegativity, or the electronegative bonds are pulling in equal and opposite directions, right? So kind of like, I know it's kind of cool to kind of tie all of that back in from these previous chapters. So small nonpolar molecules are allowed to get through. Water and glycerol, right? So small uncharged polar molecules are able to get through. So as long as they're uncharged, if they are small and they are polar, as long as they're uncharged, then a lot of times they can get through. Specifically here, we're given the examples of water and glycerol. And so water is really only able to get through because of specific cell membrane channels called aquaporins. And we'll talk about those definitely coming up in the next couple of chapters. But water is able to get through. Really what you need to know for now is that water is able to passively go through the cell membrane. Large, uncharged polar molecules, they're way too big. They can't get through the cell membrane. And we'll talk about why polarity matters in the cell membrane. Really, just briefly, the heads on these outside, you can kind of see my cursor coming through. The heads on the outside are polar, and then the inside of the cell membrane is nonpolar. And so therefore, it has to be able to dissolve in the nonpolar environment of the cell membrane in order to pass through. And so these little tiny strings, these little tails that you see, those are actually long carbon chains. So we'll talk about what a glycerol head really is, what its composition is, how we can see and tie in other things from the previous chapters into the structure of glycerol and the structure of those long nonpolar tails, okay? And so then ions, things that are charged, definitely can't get through that nonpolar environment. And proteins, massive, right? Proteins are huge compared to what we're seeing right here. Polysaccharides, right? So long sugars or long glucose monomers that are strung together, and triglycerides, those are way too big, not able to get through, okay? And so when it comes to osmosis and dialysis, and osmosis really specifically, the different concentrations of ions on either side of the membrane are described by these specific terms. And so these three terms are really just things that you'll need to memorize. It was always very difficult for me because I have to compare it to, you're comparing it to what's inside the cell versus what's outside the cell. So really when we're looking at hypertonic, hypotonic, isotonic, we're looking at comparing one thing to another, okay? And so it could be backwards, depending upon if we're comparing the inside of the cell to the outside of the cell, or the outside of the cell to the inside of the cell. So right here we're talking about a solution. So we're talking about the outside of the cell, the solution that the cell is in. And so in a hypertonic solution, we have a higher solute concentration. So what that means is if we place a cell in a hypertonic solution, then that solution will have a higher solute concentration than what is inside the cell, okay? And then the opposite for hypotonic, right? Hyper, hypo, really they just mean, hyper means higher and hypo means lower, right? Hyperglycemia, hyperthyroidism, it's really a very common prefix that you'll find in medicine. And so hypotonic means that we have a lower solute concentration. Specifically, if we take a cell and we place it into what we would consider a hypotonic solution, then that solution, the solution itself, would have a lower solute concentration than what the inside of the cell would contain, okay? And then isotonic is equal, means that we have the same solute concentration on the inside as the outside. And so here are some common electrolytes inside the body and outside the blood cell. And so these things have to be very tightly regulated. So that way we can keep this concentration gradient if we need it, or and we can use that concentration gradient to kind of use dialysis within the cell to transport things outside or to transport things inside the cell. It's extremely important in the human body. And so just a few terms before we move forward. That makes a little bit more sense for the next few slides. Osmosis is the flow of solvent through a membrane to equalize concentrations. Dialysis is the movement of solutes through a selective permeable membrane. The same goal, to equalize the concentrations on both sides. So solute particles are in constant motion called diffusion. Diffusion is really just the movement of that solute particle from one side of that selective permeable membrane to the other. So diffusion is referring to the movement of something through a selective permeable membrane. And then solutions with a different concentration gradients, they create, different concentrations on each side of that selective permeable membrane, create what we call a concentration gradient. So solute particles would diffuse from hypertonic to hypotonic. So what that means is that solutes, or solute particles, sodium chloride, let's say in water, for example, right? Sodium chloride would be the solute, and water would be the solvent. This would be an aqueous solution. Solute particles, they'll diffuse from hypertonic to hypotonic, meaning that the solute particles will go from the side that has the higher concentration, and they will diffuse through the selective permeable membrane, if allowed, to the side that has the lower solute concentration. And we call that process dialysis because it's the movement of the solutes, okay? And so if we were to look at an example of osmosis, so when solutes cannot pass through a membrane, the solvent will move instead, right? So if we have this selective permeable membrane, if we look over here on the right, I hope it's not too messy, I'll kind of try to break it down piece by piece. So if we're looking at kind of what's inside this blue box right here, I'm looking just specifically at this example. It's kind of the same thing as you see over on the PowerPoint slides. And so the movement of water, this osmosis is the movement of water going from an area of lower solute concentration to an area of higher solute concentration. Another way of saying that is it's moving from an area of higher solvent concentration, so higher water concentration, to an area of lower water or solvent concentration. So if we're looking at this example, we have the selective permeable membrane. It's important to note that in this osmosis example, the selective permeable membrane is only permeable to water, right? So osmosis, we're only allowing water to move, and the solutes that are dissolved in this solution are not allowed to move, okay? If they were allowed to move, then dialysis would occur. So these are kind of just like some laws of nature, that kind of like the laws of entropy, right? The laws of thermodynamics. We have some laws that this just always happens, okay? And so the way that we describe it is basically just through these terms. And so if we look what's inside this blue box, we have 2 moles per liter of solute on the left side and 4 moles per liter of solute on the right side. So we have a concentration. Remember, moles per liter is considered molarity. And so we have some amount of something and some volume of something. Well, we can alter the molarity or alter the concentration by changing either the numerator or the denominator. And so the way I like to break it down is when we're talking about osmosis, we're talking about the denominator, right? We're talking about changing the solvent, okay? So molarity is moles of solute over liters of solvent. And so when we're talking about water as a solvent, we're talking about osmosis, we're talking about altering the liquid on the bottom. And so as we know with like inverse proportionalities, the liquid or the volume or the solvent is inversely proportional to the concentration, right? So as we increase the volume, we're going to decrease the molarity. And you can kind of see this right here. As we increase that L, right, the volume, if we increase that, we're going to decrease that. And vice versa, right? If we increase this, then we're going to decrease the molarity. And so if we're looking at osmosis and we were to allow this water to go, it would naturally, what we call, flow down its concentration gradient in order to balance these two sides out until they're both the same concentration. They're both at 3 moles per liter, so it meets halfway. Now when it gets to that point, it doesn't mean that all of a sudden everything stops and no more water moves. It just means we're in the same thing we've talked about before called dynamic equilibrium, where for every 1 water molecule that moves from one side to the other, another water molecule moves in the opposite direction. So we still have this dynamic equilibrium where water molecules are still moving through that semi-permeable membrane, but they're moving in equal and opposite directions, okay? And so if we look on the left side, the thing that I did not include in my little schematic over here on the right, the thing I did not include is the volume, right? Is actually seeing the volume change. And so I can explain it down here on the right side in verbally, right, through terms, is in more concentration, in the more concentrated solution, we will decrease the molarity, right? If we're decreasing the molarity, then the way we're doing that is we're increasing the volume, okay? On the other side, if we have the less concentrated solution, this will increase the molarity. And we do this by decreasing the volume, right? Therefore, increasing the molarity. And it may make a little bit more sense to you if looking on the left at the PowerPoint specifically. And so if we're looking at the left, we have the semi-permeable membrane. Over here we have 0.2 millimoles and 0.4 millimoles. You know, I use 2 moles and 4 moles just to make it a little bit simpler and less decimal points. And so if we have the same volume on each side, and one of them is more concentrated than the other, and we do not allow the solute molecules to pass through. So these little purple dots are representing the solute molecules. These are not able to pass through. An important note is it doesn't matter what the solute molecule is. It could actually be 0.2 millimoles of a combination of things. It could consist of glucose and sodium chloride and potassium and all kinds of different things. Really, it's just the sum, right? It's the total solute concentration. It does not have to be the exact same solute in order for this to change, okay? And so if we have this selective permeable membrane, we only allow water to go through, then the water will travel from the area of lower solute concentration to the area of higher solute concentration, therefore successfully increasing the volume on the right until both sides have the same molarity and the same concentration. And now we would consider this an isotonic, right? Both of them have the same solute concentration, therefore they're both isotonic compared to each other. If we look at this side, on the left, the hypotonic solution is the one that has the lower solute concentration compared to solution B, which is the hypertonic solution, right? Which has a higher solute concentration compared to the left, okay? And so I know it can be a little bit confusing, but if you have any questions about that, I'll definitely meet up with you and we can get those questions answered. And so if we were to look a little bit more about osmolarity, just kind of talk about a few terms that we have and also how cells respond to osmotic, what we call osmotic pressure, right? There's this pressure for volume to change, for the water to move in a specific direction. And so it's determined by the total concentration of solutes, right? Not their identity or size. So I already kind of explained that. It can be stopped or reversed by applying external pressure. So if in this situation right here, if we were to apply pressure down on this thing right here, then it would change the direction. It could actually keep this water from moving from the hypo to the hyper. Okay, so if we were to cap this off and say put a top on solution B and put pressure, add pressure to the side, the solution B, then it can actually stop this movement and actually it could push the water in the opposite direction, right? And so it really kind of makes sense to think about it that way. That if we put pressure on this, it's obviously going to push the liquid in the opposite direction, and it's not going to care whether or not one side has a higher concentration or the other, okay? So, so the osmotic pressure is the amount of pressure needed to stop the flow of solvent. So what we consider the osmotic pressure is the specific pressure that is needed to stop that flow, right? So like I said, we can continue adding pressure and then eventually get to a point where we're pushing this in the opposite direction, but if we were to have this volume flowing through, at what pressure would we need, right? Pressure is force over area. So we have this area of the top of this solution, B. And what force would we need to push down on this to keep this from happening over here on the right side, right? And so that's what we consider osmotic pressure, okay? So the higher pressure will force solvent from the hypertonic solution to the hypotonic solution, which is the opposite direction of osmosis. And what do we call this? Very simply, we call this reverse osmosis, right? It's used to purify seawater and remove excess water in hemodialysis. So if we're undergoing dialysis and we need to remove excess water, then the machine will actually put pressure on the fluid that is flowing through the dialysis machine in order to modulate and drive that water to alter the volume to an appropriate volume that we would need to successfully complete dialysis and make sure that the concentrations in the human blood are exactly what we would need, okay? And so actually on the back of like some of your water bottles, I think Dasani like specifically, you can actually see it says purified using reverse osmosis. So now you kind of know, well, they're actually just taking all those solutes, right, that we would consider contaminants, and they're putting a semi-permeable membrane in the mix. They're only allowing water to move through, and then they're applying pressure to one side, right, to push the water molecules to the other side, and then they're collecting that other side as purified water, okay? So it's a good way to separate certain things if you need to push something through to get just the solvent, right? But if we're looking at osmotic pressure in a cell, then solutions, IV solutions, right, have to be at exactly 0.9% mass per volume saline or a 5% mass per volume glucose solution. If we have any more or any less, it could cause the cells to either shrink or explode. And so taking purified distilled H2O, right, which is just pure 100% water with no solutes involved, and we were to put that into an IV solution, it would kill the patient. And so the reason it would do that is it would cause all the cells to blow up. So why is that? Well, if we have the solution, and remember we're talking about the solution compared to the inside of the cell. So isotonic, it's very easy, right? We take a cell, and you imagine just we have this glass beaker, and we take a cell and we drop it into that glass beaker. If that glass beaker is filled with exactly 0.9% mass volume saline or a 5% mass volume glucose solution, remember, does not matter about the size or the type of solute. It's about the solute concentration, okay? And so if we have this concentration of this 0.9, we would consider this isotonic, and that is what normal saline drips are. Is we have this isotonic solution that there is going to be no net change, right? There's going to be this dynamic equilibrium. So really there should be some arrows here that point exactly the same amount of water that goes in will be the same amount of water that exits. And so it can be very tightly controlled. The cell is very happy. And then this picture down here is what an electron scanning microscope would look like of a red blood cell in an isotonic solution, right? It looks healthy, happy, and it's able to perform its correct functions. If we were to put this solution in distilled water, right? So distilled water is an example of a hypotonic solution because it has no solute involved. So therefore, it is the most hypotonic that you could really get, right? So we've got the solvent, and we have 0 moles per liter of solute, right? So that is the perfect definition of hypotonic. If we were to place a cell into that solution, well, there's obviously solutes inside of the cell, right? And so if there are solutes inside the cell, but there are no solutes on the outside of the cell because this is pure distilled water, if we were to take a beaker of that and drop that cell into there, then what we would have is water moving from the area of lower solute concentration to the area of higher solute concentration. So what would that cause? Water would diffuse into the cell. So when we're diffusing water into the cell, we're increasing the volume inside the cell. And so that cell eventually would blow up, and it would eventually rupture because it could not take the osmotic pressure that's building on the inside of the cell. The opposite would be true for a hypertonic solution, right? We take a solution and say this is a 5% mass volume saline. So 5% saline or even 4% saline would be considered hypertonic compared to the solute concentration on the inside of the cell. And so if we were to take a glass beaker and we were to drop a red blood cell into a solution that had 4% saline, then that would be a much higher concentration than the inside of the cell. Therefore, water would flow the opposite direction, right? Water would go from the inside, and it would go from the area of lower solute concentration, which would be in the inside, to the area of higher solute concentration, which would be this 4% saline solution, which would be the outside, right? So we would see these cells shrivel and shrink and eventually die because cells don't like to be shrunk up. They like to be healthy. They like to be in an isotonic solution, okay? And so in this worked exercise, we'll talk about right here, what we'll do is we will do a worked exercise for osmosis, okay? And so before I do that, I do want to include, because we were not given in the PowerPoint, so we're not given kind of a schematic like this for dialysis. So I kind of want to give an example of that, and I'll post this up, like you'll have this, that way you can reference it either while I'm going through it or even if you want to come back and watch it or listen to it or read it later, okay? So dialysis is the movement of solutes from an area of higher concentration to an area of lower concentration. So over here on the right, I have drawn this little diagram, And really what you'll see is that its solutes move in the opposite direction that you would expect water to move in osmosis, right? So if we have the selective permeable membrane, it's important to note that in this situation, for dialysis, the selective permeable membrane is only permeable to solutes. So therefore, water is not able to pass. If it was able to pass, then what we would see is this up here, right? And if solute and water were able to pass, we would see a very quick reaction to they would both jump straight through. It'd almost just be like putting them in a beaker together with no membrane at all, right? They would immediately mix together and diffuse to be a homogeneous solution. Excuse me. And so in this situation, in dialysis, what we would have if we had a 2 mole per liter solution of, doesn't matter what it is, say sodium chloride glucose mix, 2 moles per liter on the left and 4 moles per liter on the right, what we would see is the solutes would move from the area of higher solute concentration to the area of lower solute concentration. It's important to note that this would not change the volume, right? Because the volume of solute is extremely small compared to the volume of solvent, okay? And so when the water moves, the volume moves, it's actually changing the volume on those, right? So in dialysis, we can think about it about changing the concentration, which would eventually change to be in this dynamic equilibrium for every one solute molecule, it moves to the right, another one would move to the left, right? And so eventually we would get to this dynamic equilibrium. And so the way you can think about this is in the more concentrated solution, we will decrease the molarity, right? Because the solute is leaving. Therefore, we're decreasing the number of moles, and therefore the number of moles is directly proportional to the molarity, right? Because it's on the top, it's the numerator. So we're changing in dialysis, we're changing the numerator of molarity. And so we're decreasing the moles, therefore decreasing the molarity. And so the more concentrated solution will become less concentrated. The opposite is true for the less concentrated solution. So we're increasing the moles, right? Because the moles are coming from the more concentrated and they're entering the less concentrated solution. Therefore, we're increasing the moles of that solute and we are successfully increasing the molarity, okay? And so if we were to jump back over to this PowerPoint and we were to look at this, worked exercise for osmosis, I've written these questions out on the right. That way I don't have to flip back and forth. That way you can see them. I have already answered them, but I will go through them. So in this solution, which is the hypertonic solution, right? And so if you do want to like cover this up or not look at it and then try to answer these yourself and see if you got them right, that's not a bad idea. But with this, in solution A, we have 0.01 mole per liter of glucose and 0.02 moles per liter of sucrose. Therefore, combined, we have a 0.03 mole per liter solution, right? Like I said, it doesn't matter what it is, what the solute is or what combination of solutes we have. It's the overall concentration. And solution B, we have a 0.02 mole per liter solution of sucrose, okay? And so therefore, 0.03 is a larger number than 0.02, and therefore solution A is hypertonic compared to solution B. And then which one's hypotonic? It's the exact opposite, right? Solution B is hypotonic to solution A. So question number 3, if the solutes cannot pass through the membrane, so if we can pause right there, we automatically know, okay, we're talking about osmosis, right? Which direction will water diffuse? What is this process called? So obviously this process is called osmosis, right? Because we're talking about the movement of the solvent, which would be water, and not the solute, because the solutes in this situation are not able to pass because it's given, that information is given to us in this question. And so which direction would the water diffuse? So the water is always going to diffuse to even out the concentrations, right? So they would eventually move to where we have 0.03 on one, 0.02 on the other. They would eventually come to this dynamic equilibrium of 0.025 moles per liter on both sides if water were able to pass, okay? So that they would meet right in the halfway middle mark. So which direction would water move? Well, water would diffuse from solution B to solution A, right? So just like the definition shows, we're going to change, alter the denominator of molarity, and we're going to decrease the volume in solution B and increase the volume in solution A, right? And so as we're decreasing the volume, we're making solution B more concentrated to go up to 0.02, we're making solution A less concentrated by diluting it, right? So you can even think about this like back to your C1V1 equals C2V2. You add volume, you're diluting it. You're decreasing the molarity because you're increasing the volume, which is the denominator in the equation, right? So after osmosis, which solution will have the greater volume, right? So if water is moving from B to A, then it makes perfect sense that solution A would have a larger volume at the end of this, okay? And so that's really it for chapter 9, for chapter 8. So we have this whole chapter summary. Like, these summaries are awesome. I definitely suggest going through those to get really like extrapolate the super important information. And so I'll bring chapter 9 over, and we will begin and we'll go through just the first part, so chapter 9.1. So we'll go from chapter 9.1, which is just discussing acids and bases. And so chapter 9, really the whole overview, the big premise is acids and bases. What's an acid, what is an acid, and what is a base, right? How do we solve problems with acids and bases? What happens when we mix them together? And then pH, we're talking about what's the negative log of the hydrogen ion concentration. And that'll make a lot more sense when we talk about what is an acid, what actually is an acid. And then acid-base neutralization reactions. If we have an acid and we want to neutralize it and bring it to a pH of 0, how much base do we need to add? Well, it depends upon the hydrogen ions. And then buffers. Buffers will relate to the carbonic acid buffer system in the blood, and we'll relate it to a little bit more of biochemistry as we start to bridge into chapter 10 and 11, and that's really getting into the biochem stuff. So this is like the last little bit of math, really test number 3 is not going to include a whole lot of math. Really, this is like the extent of the math that we're going to include is with the pH stuff. And so we're slowly weaning away from the math, okay? So if you found test number 2 a little bit easier, then have no fear. It should be very similar moving forward. And so acids and bases, right? Introduction to what is an acid and what is a base. So we have a few definitions that we have to memorize, okay? So they're defined by their behavior in water. And so an acid and a base will behave differently depending upon how it is added to. So when it is added to water, they will behave differently. And so we have this first definition that we'll introduce, and so this is probably the easiest one to understand. And so according to the Arrhenius, so we call this the Arrhenius definition of an acid is a substance that produces hydrogen ions in water. And so if we look over to the right, we're really looking at, pure water has 1 mole of oxygen for every 2 moles of hydrogen. And it makes sense, right? Every water molecule is H2O. We have 2 hydrogens and 1 oxygen. And so therefore, if we're increasing the proportion of hydrogen ions in that water, then we're going to be increasing the acidity, okay? And that is the Arrhenius definition, right? So it's a substance that produces hydrogen ions in water. So an acid increases the hydrogen ions, right? So what does a base do? Well, it does the opposite. It increases the hydroxide ions, the OH, okay? So you think about taking a water molecule, breaking it apart, and having the OH portion and the H portion, right? So an acid is going to pump up the hydrogen ions, and a base is going to pump up or increase the what we call hydroxide ions, okay? So this is an OH, and so if you need to draw like the Lewis dot structure for OH, I definitely suggest doing that, making sure that you kind of know what that looks like, but really what we'll use is we'll just kind of draw this OH with a negative sign on it, okay? And so a hydrogen ion always bonds to a water molecule in a solution to form what we call a hydronium, okay? So if we have H2O and we have pure water, pH of 7, completely neutral, and we start adding an acid, and we start adding hydrogen ions to that solution, then we're going to increase the proportion of hydrogen ions to where now we've got more than 2 hydrogens per oxygen atom, right? So these hydrogens don't like to just float around by themselves, they like to jump onto water molecules. And so what happens is we get this H3O, okay, and we have a specific name for this. This is called a hydronium ion, okay? And you can see over here on the left, this PowerPoint, we have a hydrogen ion, which we consider a proton. And I'll talk in just a second about why we call that a proton. We add that to a water, we get what we call H3O. It has a positive 1 charge, and if we were to do the formal charge for it, if I kind of like zoom in right here, if we were to do the formal charge for this hydronium ion, we can see that oxygen wants to have, right, so this hydronium molecule, oxygen owns 1, 2, 3, 4, 5 electrons. Oxygen wants to own 6. If we look at the periodic table, hopefully that'll kind of jog your memory about why it wants to own 6, because it's in its valence shell. Therefore, in the hydronium ion, it owns 1 less than it wants to own, and therefore it has a positive 1 charge, right? It's lacking 1 electron, okay? And so the reason we call this thing a proton is these are all the exact same thing, okay? So what is a hydrogen? Well, a completely neutral hydrogen atom has 1 proton, 1 neutron, 1 electron, okay? So what does a hydrogen ion have? Well, if it's a positive 1 charge, then it's lacking an electron. If it only has 1 electron to begin with, then now it has 0 electrons, right? So therefore, a hydrogen ion, this H+, is just 1 proton and 1 neutron stuck together, okay? And so these are all the exact same things. So when we're talking about these things, to kind of remember, when we draw this H+, remember this is really what we're talking about. And so a hydrogen ion is 1 proton and 1 neutron. It's kind of like drawing a little figure here. It's a positive charge and a neutral charge stuck together. We also draw it as H3O when it is in water. Or we can say H3O positive, right? So this is like the actual Lewis structure. Or we can call this a hydronium, right? And I guess I forgot to put in here hydrogen ion, right? So if I say hydrogen ion, I say hydronium, I say proton. When we're talking about acid-base chemistry, these all mean the exact same thing. And so the Arrhenius definition of a base, kind of like I just said, it's something that increases the hydroxide ions in solution. And so there are a lot of strong bases are these group 1 and group 2, or 1A and 2A metals bonded with a hydroxide ion. And if we remember, the alkali metals, that group 1A, all lose 1 electron to be like the noble gases. Therefore, they have a positive 1 charge, right? So alkali metals have a positive 1 charge. Alkali earth metals lose 2 electrons, right? Because they're in that 2A column. And so therefore, they have a positive 2 charge, right? And so sodium hydroxide, it makes sense why it would only have one hydroxide. And the reason for that is because hydroxide has a negative 1 charge. And if you want to draw the Lewis-Dot structure out for that, you'll see that hydroxide, the negative 1 charge, is on the oxygen atom, right? So in that situation, the oxygen has 2, 4, 6 electrons that are non-bonding, and then it has 1 pair of electrons that are bonding to the hydrogen, and so therefore it has 1 additional electron than it wants to have, so therefore it has a negative 1 charge. And so then if we look at, like, say, calcium hydroxide, right? Right over here on the right side with the blue box, you can see for a calcium we're going to have 2 hydroxides, right? So calcium dihydroxide. And so calcium hydroxide is a very, very common base. And so a lot of these are very strong. And what we call these are hydroxide-containing salts, okay? So these are salts because these sodium, so for example in here, the sodium and the hydroxide are ionically bound together, okay? But the hydroxide, the bond between the oxygen and the hydrogen in the hydroxide is a covalent bond, okay? But the sodium and the hydroxide are ionically bonded together. So it's kind of like one of those examples of what we call the polyatomic ions, right? So this hydroxide would be considered a polyatomic ion. It contains an oxygen and a hydrogen, 2 atoms, more than 1 polyatomic, okay? So when a proton from an acid is combined with a hydroxide ion from a base, a water molecule is formed, and that's what we call a neutralization reaction. So if we have an acid and then we add a whole bunch of base, then, I mean, think about the Arrhenius definition. We have a whole bunch of hydrogen ions, and then we add a whole bunch of hydroxide ions. Well, we've got the makings for water, and both of them are opposite charges of one another, and so they're obviously going to jump together to form this water. So then, over here on the right, where I kind of have slide 5 written, you can see sodium hydroxide plus HCl, for example. This hydrochloric acid is an acid. You can see that this acid is an acid because it's going to add hydrogen ions to the solution. Sodium hydroxide, we've already talked about why it's a base. These will always create water and a salt, right? In this situation, it's table salt. So literally, if you took like 1 mole of sodium hydroxide, 1 mole per liter sodium hydroxide, and 1 mole per liter of hydrochloric acid, you added them together, you would get a pH of exactly 0. I'm sorry, a pH of exactly neutral, pH of exactly 7, right? So neutral being 7, and you would get water plus a salt. And that is true for all acids and bases that are added together. Okay, and I kind of drew this like intermediate, if that kind of helps you understand what's going on. The sodium and the hydroxide fall apart. Same for the hydrogen and the hydrogen ion and the chlorine or the chloride ion fall apart. These two bond together to form sodium chloride, and these two bond together to form water. Okay, so an acid plus a base equals a water plus a salt. Okay, and that is true for all acids and bases added together, all strong acids and bases added together, and this is called a neutralization reaction. So another definition that we have is called the Bronsted-Lowry definition. This has to do with donating or accepting hydrogen ions. So in this one, we're not talking about hydroxide ions, we're only talking about hydrogen ions. And so therefore, an acid is a hydrogen donor, and a base is a hydrogen ion. So an acid hydrogen ion donor, a base a hydrogen ion acceptor. Acids become conjugate bases, and a base becomes a conjugate acid, okay? And so that's when we're talking about the Bronsted-Lowry definition of acids and bases, all right? And so the definition makes it possible to see how molecular compounds behave as bases. Ammonia, in this situation, is a base because it will accept a proton from water. And so water can act as an acid or it can act as a base, depending upon whether or not it is accepting a proton to become a hydronium, therefore acting as a base, or it is donating a proton to become a hydroxide ion, therefore acting as an acid. So most things, many acids can act as bases. And so when we get into like the diprotic acids, like hydrochloric acid, we'll talk about how some of them are acids and bases, but it depends upon how we're talking about it. It can be an acid or a base, right? So in this situation, we can see, using the Bronsted-Lowry definition, we can see this ammonia is the base. Why is it the base? Because it is accepting a hydrogen ion, okay? The hydrogen ion has to come from somewhere, so where is that hydrogen ion coming from? It's coming from the water, which is acting as an acid, right? And so therefore, we're getting a hydroxide ion and an ammonium ion. And so it's important to note that when we're talking about Bronsted-Lowry definition, adding an acid and a base together, these definitions are a little bit different than the Arrhenius definition. The Arrhenius definition, when we add an Arrhenius acid and an Arrhenius base, we always get a water and a salt. When we add a Bronsted-Lowry acid and a Bronsted-Lowry base, we don't always get an acid and a salt, right? Because there's no salt. We don't always get a water and a salt because there's no water and there's no salt here, and you can see this base and this acid. And it's all just based on how we define what is an acid and what is a base. And so it's important to kind of distinguish that an Arrhenius acid and Arrhenius base added together will form water and salt, right? But it's not always true for a Bronsted-Lowry acid and a Bronsted-Lowry base, okay? And so conjugate acid-base pairs, right? So after transferring a proton, the acid is known as a conjugate base. Why? Because now it can accept a proton. And so remember, we're still talking about Bronsted-Lowry here, all right? Proton acceptors and proton donors. And so after this, this base right here, this ammonia, right? So I'll zoom in on this ammonia right here. This is the base, right? What is a base when it comes to the Bronsted-Lowry definition? It is a proton acceptor. Therefore, it has accepted a proton. Well, now, what can it do? We've got this double arrow right here, right? Which means it can go one way or the other. So therefore, now this ammonium ion is a proton donor. So therefore, it is now a Bronsted-Lowry acid by definition, right? Acids are proton donors. And so what we call this is, we don't just call it, oh, now it's an acid. We call it the conjugate base, right? So we have the conjugate acid, right? So we have the base, which is the ammonia, and the ammonium ion is now the conjugate acid. And then the acid becomes a conjugate base, right? So water turns into this hydroxide ion, which can now accept a proton. What is a proton acceptor? According to Bronsted-Lowry, it is a base, right? So now we have this conjugate base. This hydroxide ion is now a conjugate base. And so therefore, we always have a conjugate acid, conjugate base pair, right? So for that's what we call it, acid-base pairs, acid-base chemistry, right? So after transferring a proton, the acid is known as a conjugate base. After accepting a proton, it is now known as a conjugate acid. So an acid and its conjugate base, and a base and its conjugate acid, are known as conjugate acid-base pairs, right? And so a molecule that can act as either an acid or a base is considered amphoteric, okay? So that's just really an important term to know and to memorize. Amphoteric just means something that can act as an acid, right? A Bronsted-Lowry acid, or it can act as a base, right? Or Bronsted-Lowry base. So if we're looking at this situation, we have acetic acid or acetic acid. So acetic acid, everybody should know what this functional group is right here, right? It is a carboxylic acid, right? So we have this carboxylic acid. Yeah, now, so obviously now it makes sense why we call it, why is it called a carboxylic acid? Well, it's called a carboxylic acid because according to Bronsted-Lowry, it can donate a hydrogen, right? And so then we've also talked about how this carboxylate, right? So now we have this acetate ion, okay? And so what is this acetate ion or a carboxylate functional group? Now it is a conjugate base because it can accept a proton from water, okay? And so here we have conjugate acid-base pairs, conjugate acid-base pairs. So we have acetic acid now turning into the acetate ion. It is now a base. And now we have the water, which is a base, now coming into the conjugate acid, right? So very easy, makes sense. If you have problems with it, definitely let me know. So another one here, this is just going back to the one at the beginning. And so here is a list of common acids in biochemistry and medicine. And so these are, I'm not too concerned with y'all memorizing the name, the structure, exactly where it's formed, like biological role. I'm not as concerned about that, but if I give you phosphoric acid and I give you the Lewis dot structure for that, you should know that there are 3 protons that can be removed from that thing. You should know that it is an acid. You know that if I give you a phosphoric acid or a phosphatate, right, ion, and the hydrogens are gone, then you should know that that is a conjugate base of phosphoric acid. And you should know we're talking about Bronsted-Lowry definitions, okay? And so as this pertains to acid-base chemistry, and more specifically Bronsted-Lowry definitions, is the extent to what I would like you to know for this. When we get into chapters like 10, 11, 12, if we get to 13, then yes, I'll ask you a little bit more about like the biochemistry, like memorize the structure of acetic acid, right? Know what that functional group is. Know if I were to give you a biological process, know why it's important for it to be in a specific pH and that sort of thing, okay? But for now, with these 2 charts, I just would like you to look at them as information purposes and to know specifically why they're considered conjugate acids, conjugate bases, which protons are leaving, which protons are considered acidic protons, how you can use Bronsted-Lowry definitions to apply them to these situations. So then we'll work through this last exercise. I'll talk about the strengths of acids and bases. We'll pull together Le Chatelier's principle, and then that'll be it, okay? And so for this problem right here, I worked it out for slide 12. It's over here on the right. So is HF, so hydrofluoric acid, acting as an acid or base? I guess I kind of gave it away, but anyway, it's written right here, right? So is it acting as an acid, or is it acting as a base? Well, considered, and we're looking at Bronsted-Lowry definitions here, right? So is it considered an acid or a base? It's considered an acid because right here you can see that it is donating a hydrogen to water. Therefore, this right here, this right here is considered the acid, okay? And so therefore this F minus, which it's missing all of its dots around it, it's got 2, 4, 6, 8 valence electrons that are non-bonding around it. That's why it has a -1 charge, because fluorine wants to have 7. So therefore, this is the conjugate base of hydrofluoric acid, is this F minus, or this fluoride anion, okay? Water, it's acting as a base. It's a hydrogen ion, or it's a hydrogen acceptor, okay? So considering Bronsted-Lowry again, this is a hydrogen ion acceptor. Water is acting as a base in this situation. So what are the conjugate acid-base pairs in this reaction? So the acid is HF, the conjugate base of HF is just the F minus, so the acid is hydrofluoric acid, the conjugate base is the fluoride anion. What is the base? It is the water, right? What is the conjugate acid of that base? It is the hydronium cation, right? So pretty simple, pretty straightforward. So strengths of acids and bases, this is an important concept. It is kind of like important, and also one of the reasons that that last chart wasn't too concerned with you memorizing, because those aren't actually considered strong acids. So what is a strong acid and what is a strong base? Up to this point, we've just talked about hydrogen ions disassociating from acids. Excuse me. So that's not always the case, right? So a hydrogen ion won't always disassociate because maybe it's more stable for that hydrogen ion to stay on the acid. So what about a carboxylic acid? Well, if it's a super low pH and there's all these hydrogen ions floating around, and we'll talk about Le Chatelier's principle in terms of that, then it's more stable for that hydrogen ion to just stay on the carboxylic acid and to not disassociate. So therefore, it's not considered a strong acid, okay? So a strong acid, by definition, and a strong base, they're classified by the extent to which they dissociate in water. So hydrochloric acid, HCl, is a very strong acid. It will disassociate completely in water. So what that means, right over here on the right, slide 13, what that means is that for every 1 mole of HCl added, we will have 1 mole of hydrogen ions added to the solution. Okay, so that makes sense because it will disassociate completely, right? So for every 1 mole of HCl we add, we will have 1 mole of chloride anion and 1 mole of hydrogen ion, right? And it will disassociate completely. It makes the math very, very easy when we start getting into talking about calculating pH. So strong acids and bases disassociate completely. Most strong bases are hydroxide salts with the group 1A or 2A metal cations. So if you see an alkali metal or an alkali earth metal, so that first column or second column, then you can automatically, almost always, assume that it is a strong base, okay? And so here's a list of strong acids and strong bases. And so I would like you to memorize this list. I'm not too sure, it may be on your cheat sheet, or I hate to call it a cheat sheet, but on your formula sheet for the test. If it isn't on there, I'm tempted to add it. I'll touch base with you before the test. But for right now, it would be important to go through and say HNO3, that is considered nitric acid. What's the conjugate base? The conjugate base is very easy to memorize, right? We just remove a hydrogen and it's got a -1 charge. What about strong bases? You can see that most of these are group 1A or group 2A metals, right? So calcium, potassium, sodium, all of these are group 1A or group 2A metals, and they have their respective hydroxide ions, right? So Ba obviously has a charge of +2 because it has 2 hydroxides. And remember, these are all ionically bonded together, okay? So the OH, the bond between the oxygen and the hydrogen, is covalent. The Ba and the O8 and the 2 hydroxides are ionically bonded together. These are electrostatic interactions. In acids, these are covalently bonded together, okay? So the hydrogen is covalently bonded to the SO4, right? So that's a little bit of a difference between acids and bases. But these, the big thing is, memorize these, know their structure, and then know that they disassociate completely. So if I say I just added 1 mole of HCl, then you know that I just increased the concentration of hydrogen ions by 1 mole, okay? So let's do this worked exercise, and then we're kind of getting to the end of this as well. So nitric acid, HNO3, is a strong inorganic acid used in the laboratory. And look, it's right here on this chart, first one on the chart. So write the chemical equation that shows the reaction of nitric acid and water. Label the conjugate acid-base pairs. So very easy. Remember, we're still talking about Bronsted-Lowry right here, right? Hydrogen donors, or hydrogen ion donors, hydrogen ion acceptors. So we can write this out. HNO3 plus H2O is going to go to its conjugate base, which is NO3 minus, plus the conjugate acid of water is always going to be H3O, right? So the conjugate acid of water, always H3O positive, right? Or hydronium is the name of that thing. Conjugate base to water, hydroxide ion, right? Just OH negative. So here are the conjugate acid-base pairs, okay? So strengths of acid and bases. Weak acids and bases undergo reversible reactions of water that favor the reactants. So it means that they will not always disassociate. Some of them will, but not all of them, okay? So acetic acid, it is a weak acid. We have this carboxylic acid. Carboxylic acid is usually a weak acid, regardless of what it is attached to. Sometimes it can be strong, but it's usually a weak acid. So if we have this reaction with water, we can see that this is the weak acid, therefore this is the conjugate base, and we call this the acetate ion. Hydronium is the conjugate acid of water, and so it favors the reactants. That means that at equilibrium, we will not have the same number of these and the same number of those. In a strong acid, we will have almost no reactants, right? Because they dissociate completely. In a weak acid, we will have more reactants and less bases. More reactants and less products, right? So less conjugate bases, I think is where I was head was at. So we can apply Le Chatelier's principle to this whole thing, right? So when a reaction is at equilibrium and it is disturbed, the reaction responds by shifting to restore equilibrium. Definition of Le Chatelier's principle. So what happens if we have a weak acid, right? Like pyruvic acid. It's a very important biomolecule. Pyruvate, super important for producing ATP and high energy bonds that can be used through the citric acid cycle, right? Pyruvate oxidation and the citric acid cycle to produce hydrogen ions that will eventually be used to produce ATP. And we'll talk a little bit more about that in the biochemistry stuff, okay? So kind of the last thing here, Le Chatelier's principle, if we add hydrogen ions, right, so we add H3O, then it will push this reaction to the left, okay? So it'll push it to the left, therefore producing more pyruvic acid. If we were to add more water, it's going to push this reaction to the right to produce more pyruvate, right? The weak conjugate base, and produce more of this hydronium ion. So it's basically using what you already know about Le Chatelier's principle and just applying it to acid bases. So let's do this last worked exercise. I'll make a few announcements and then we can go on our way. So consider the reversible reaction which occurs in our blood, shown below for the weak acid carbonic acid. So this is the carbonic acid buffer system. We'll talk a little bit more about this and its extreme importance in diabetes and a lot of other things. There's a lot of implications and very important to know, especially for medicine. So question 1, does an increase in carbonic acid cause the shift to the left or to the right? And let's explain. How does this change the concentration of hydronium ion? So therefore, how does it change the pH, right? Does it make it more acidic or less acidic? So if we add more carbonic acid, we know that this over here on the left on the reactants that I'm circling with my mouse is the carbonic acid. How do we know that? Because it has its hydrogen attached. This does not have that hydrogen attached, right? So this right here, this hydrogen right here is been removed. Therefore, this is the conjugate base, right? This is carbonic acid. This is the conjugate base, carbonate. Okay, so this is carbonate, right? So if we react it with water, if we increase this, we're increasing the reactants. We will therefore push it to the right, right? How does this change the hydrogen ion concentration? It's going to increase the hydronium because we're increasing the products, right? So a very simple way that we can take what we know about the Le Chatelier's principle and apply it to this. So the second question, does a decrease in carbonic acid cause a reaction shift to the left or the right? How does it change the hydronium ion concentration? If we decrease this, we're removing reactants and it will push to the left to compensate. If it's pushing to the left, then we're decreasing the products, and hydronium is a product, so therefore we're decreasing the hydronium ion, okay? So I kind of have that outlined right here. This will be uploaded so you can see that. And so that's all that I have, and we'll talk about pH. And we'll do 9.2 forward, as you can kind of see at the bottom right here. We'll do 9.2 forward on Friday in lecture. I'll take the first kind of 5 to 10 minutes to answer any questions about this, getting up to this point. Again, like, super sorry about missing. That has never happened before, and will definitely never happen again. I think I just stretched myself a little bit way too thin for the last couple of days. Actually, really for like the last couple of weeks. And so this weekend I didn't have a chance, so it really all just like caught up to me, and I woke up feeling pretty bad, pretty sick. But I feel better, and so I'll be ready to roll early on Friday. And so that's all I have for the content. A few announcements. So lecture Friday, we'll do 9.2 and we'll move forward from there. We'll take the first couple minutes, first 10 minutes, 5 minutes to do questions. I'll show up 10 minutes early to give you back your exam. So I will finish grading the exam. It will be in the grade book by the time that you walk in to class on Friday morning, and I will hand that back to you. And so therefore test corrections, right? So we will do test corrections again. I think test corrections are extremely useful, and they help you, they honestly help you do better on the exam. They help you figure out how to critical think through the questions and how to apply what you know and what to expect and how to study. Really, it's like a lot about what to study. So the test will be returned to you, so therefore test corrections. I thought about it after writing this, but I didn't want to rewrite this entire page. So test corrections are going to be due on Friday 11/2. That gives you 1 full week to do your test corrections. Like last time, it will be counted as a quiz grade. So please, if you did bad on the test corrections on the last one, I look for very specific things. How much effort was put in, right? So if you got a bad grade and I only get like 2 pages of test corrections, I know that you didn't put as much effort as you really should have or could have put in, right? So I know things get busy. That's why you get 1 drop, right? So one of those quiz grades does get dropped at the end of the semester. Keep in mind that it is already dropped in the system. So whatever grade you see includes the lowest dropped, right? And so those test corrections, I'll give you 1 full week. The reason I do that is some may have more more to correct than others, right? So if you want to turn those in early, like that's perfectly fine. You want to bring them to me Monday, the following Monday, that's perfectly fine. Just whenever you get them, just by Friday at the beginning of class, for whichever class period you're in. I think honestly what I'll probably do is really they're going to be due whether you're in the 8 a.m. or the 9:05. I will count them late if they are not given to me by 10 o'clock or 10:05. I'm sorry, 9:50. 9:55 a.m. So that's when the 9:05 class ends, right? It's a 50-minute class, 9:05 to 9:55. So if you're in the 8 a.m. and you can get those to me by 9:55, let's just round to 10. If you can get those to me by 10, then I will count those as there. Okay, so I'll stick around there from if my class finishes up a little bit early, I'll stick around and I'll take those test corrections on Friday of next week. Okay, so this is Friday of next week. So this is not this coming Friday because obviously you won't even have your test. So homework, I'm going to open it as soon as I upload this, as soon as I get this recording stopped. I'm going to go through. What it will be on is all of Chapter 8 and Chapter 9.1. So basically everything that we've done in Chapter 8 and what we did today in Chapter 9.1. I will be opening up a quiz on Friday. It will include Chapter 8 and what we have gone up to in Chapter 9. So I really kind of want this quiz to be more of like a helper's guide to answering questions that are test-like, okay? So what I'm going to do is I'm going to work on that on Friday. So it'll be open probably Friday evening after I've had a chance to polish it off, since I'm prioritizing the test correction or the grading the test first. So this is likely going to be take-home, open notes, untimed. It will most likely be long though. Okay, so it will be something that you will have to put a good bit of work into. But I think it'll be good to help maybe give you a little bit more difficult questions and then give you unlimited time to work on it. That way when you're kind of under the clock for the test, you're a little bit more prepared for what type of questions I could actually ask you on Chapter 8 and 9. Chapter 8 and 9, it's not a super difficult chapter, neither of these. 9.24 it is, but really it's a lot of definitions. I'll do my best to incorporate some critical thinking into those questions. But those will be due on Wednesday. It will be a Canvas quiz. So I will give you a Canvas quiz. It will be due on Wednesday, 10:31. And so that'll be due next Wednesday. So really big things to remember. Homework opening up today, due on Tuesday. Okay, so I'm giving you one extra day because it's opening up so late. Excuse me. It will be due on Tuesday. Okay, so it's opening up momentarily within the hour. Tests will be graded and returned on Friday. Corrections due in a week from the time you get it back on Friday. Quiz will open on Friday, but it is due in less than a week. It is due on Wednesday. Okay, so kind of keep these things in your calendar. I will post an announcement as soon as this is uploaded saying, hey, it's uploaded, and I'll include these in that announcement. That way you have all that information. So, as always, if you have any questions, definitely email me. I am free to meet. Friday, if I need to meet with y'all on Friday, I can come to campus tomorrow, Thursday, but it would just have to be roughly after about probably 8:30 p.m. And I could stay as long as you need me to. Just remember I do have to get up to get there at 8 a.m. on Friday. So if you need any help, definitely hit me up. Friday, I'll be on campus. Class finishes at 10. Best time to catch me really would be between 4 and I'll stick around a while on Friday. So I'll stick around until about 9. If you absolutely need to talk to me, need to see me, and you're leaving campus before 4, right? So you're like completely willing to come after 4, but there's no way you can come. That's fine. Just email me. I will make time, right? So I will stop whatever I'm doing to make sure that I can get there to help you. So if you absolutely need to see me sometime between roughly 12 and 4, if there is a time that you need to see me, just send me an email and I will make time for you. Okay. So all right, y'all. That is it for right now. If any of y'all have any questions, shoot me an email. Sorry about this morning. I really hope that this makes up for it. and I will see you all Friday. See you all later. Have a great evening.